Welcome to heat transactions. The change in internal energy for a system is given by this equation here, where we have du, the infinitesimally small change in internal energy, is equal to dq, the infinitesimally small amount of heat transferred between the system and the surroundings, plus dw sub exp, so this is the expansion work done, plus dwe, where we is the extra work done, the non-expansion work done by the system. A system kept at constant volume can do no expansion work, and that means that the expansion work done is zero. And if the system is incapable of doing any other kind of work, then dwe is also zero. And in this case, where no work is done, either expansion work or extra work, then the change in internal energy, du, is equal to the heat transferred, dq. That is, any change in internal energy must come from heat flow. And we can write this as a measurable change at constant volume, where the subscript on Q sub V here indicates the change occurs at constant volume. So delta U is equal to Q sub V. And that means that if we measure the energy supplied to a constant volume system as heat, or released as heat, then we are measuring the change in internal energy. And this now brings us to calorimetry. So calorimetry is the study of heat transfer during a physical or chemical process. And a calorimeter is a device that we use for measuring the energy transferred as heat. So one of the more common calorimeters that we use, and a very accurate one, is the adiabatic bomb calorimeter. We've got a bomb calorimeter that looks something like this. We have an outer jacket here that contains some water, a nice water bath for us. We've got a thermometer measuring the temperature of that water. Inside the water bath then, we have our bomb, which is this metal-lined container. Inside the bomb, we've got some oxygen at some specified pressure, and we have our oxygen input there. We have our sample sitting in a crucible here that we've got some electrical firing leads going into, and when we apply a voltage difference across those firing leads, we can then combust that sample, and the sample can be either solid or liquid. And because we've got plenty of oxygen around, because we've got it under a relatively high pressure, then there's plenty of oxygen for our sample to combust. That combustion reaction releases heat that goes out through the metal walls of our bomb and heats up the water surrounding the bomb. We can then calculate how much heat was released if we know the heat capacity of our bomb calorimeter. So the change in temperature delta T of the calorimeter is proportional to the energy that the reaction releases or absorbs as heat. So Q is equal to C delta T, where capital C is the calorimeter constant. So the calorimeter constant C, which is really the heat capacity of our calorimeter, can be determined by passing a constant current I from a source of known potential difference, delta phi, for a period of time t, in which case the heat imparted into our calorimeter is equal to Q is equal to I times T times delta phi. Alternately, we could determine the heat capacity, or the calorimeter constant C, by burning a known quantity, so known mass, of a substance with a known heat output. So, if the temperature of a system is increased at constant volume, then the internal energy of the system increases. And if we plot the internal energy U as a function of temperature, so we've got U versus T, then the slope of that curve at any temperature is the heat capacity of the system at that temperature. And note that the heat capacity may be different at different temperatures. So the heat capacity at constant volume, C sub V, is given here. So C sub V is equal to the partial derivative of the internal energy with respect to temperature at constant volume. So note that the internal energy varies both with the volume and with the temperature, but the volume is being held constant here as denoted by that V outside the parentheses. Now, the heat capacity is an extensive property. That is, 100 grams of water requires 100 times as much energy as 1 gram of water does to raise the temperature by the same amount, say 1 degree. The molar heat capacity at constant volume is labeled C sub V, comma M, and this is the heat capacity per mole of substance, the constant volume heat capacity per mole of substance. And so the molar heat capacity at constant volume is simply the heat capacity divided by the number of moles. And note that the molar heat capacity at constant volume is an intensive property. Now, the specific heat capacity, or C sub V, comma S, is the heat capacity per unit of mass, normally per gram. So the specific heat capacity is the heat capacity of some sample divided by the mass of that sample. In general, the specific heat capacity depends upon temperature and decreases at low temperature. At room temperature and above, the variation in specific heat capacity is generally fairly small. And that means that we usually ignore the variation in heat capacity as long as we're dealing with temperatures around room temperature. Now, the heat capacity is the proportionality constant for the internal energy versus temperature curve. So du is equal to C sub V times dt. If the heat capacity is independent of the temperature over some measurable temperature change, then we can say that delta U is equal to C sub V times delta T. Now, because we know that delta U is equal to Q sub V, that is, the internal energy change of our system is equal to the heat transferred at constant volume, that means that now we can write Q equals C delta T, fixed at constant volume. So a large heat capacity implies that for a given quantity of energy transferred via heat, there will be only a small increase in the temperature. An infinite heat capacity implies that there will be no increase in temperature when heat is absorbed. Now, at a phase transition, the temperature of a substance does not increase as energy is added as heat. And that means that at a phase transition, the heat capacity of our substance is essentially infinite. So that was heat transactions.